Nature provides us with many energy sources. Some, like chemical energy and fossil fuels, have proven to be problematic. The kinetic energy in wind and the photonic energy in light have proven to be powerful ways to energize our civilization. One source that we've yet to tap into is the energy in ocean waves, which theoretically could supply over 60% of the US's electricity needs. The only problem is that no one has yet to produce a commercially viable wave energy converter, though many have tried. Today, we're going to visit Oscilla Power, a startup in Seattle, Washington, and learn about their concept to generate electricity from the power of waves.
My name's Tim Mundon. I'm the Chief Technology Officer for Oscilla Power, and I'm going to give you a little walk around our facility here in Seattle. Through here, we've got laboratory and workshop, so come and have a look. So probably one of the first things to start with is actually a little talk about the technology. So what we have here are some smaller scale representations of our Triton wave energy converter that we've tested over the years. So over at the back, you've got also a bit of a history of, the different designs and different changes over time that we've gone through. So on the back here, which you can kind of see here, is 60th scale of our megawatt system. They all have the same fundamental principle. They all have this floating body, and hanging beneath it, you have some people call it a heave plate, we call it a reaction structure or a heave ring. But this is unique to our approach, is this ring-shaped structure, and it allows us to be able to capture energy in multiple modes of motion. So this is classically known as a two-body wave energy converter, whereby this moves up and down in the waves, and then this resists its motion. And this can also be in any water depth, because it's ultimately referenced from the surface. The big difference that our technology has is that because it has these three drivetrains and three lines connecting to a ring, any motion of the float, whether it be pitching, rolling, heaving, twisting, yaw, all of them, surging and swaying, they all translate to relative motion. And that relative motion can be extracted in the drivetrains. The key thing here is not to look at what's on top, because when we build small scale models, we have to do whatever we need to in order to get representative kinematics and dynamics. The relative motion between the two bodies needs to be representative of the full scale system. So they'll all look a little bit different on the top. But the key thing is that the shape is what we're trying to test. Now, this particular system, this is the most recent tank tests that we did. And this one is actually fully representative on the top as well. And this is because our survival strategy is actually to submerge the system fully below the surface. This is actually designed to be fully submerged in the tank, so we can actually test how it works underwater as well as on the surface. So what happens is that when the system goes below the surface, the loads on it reduce significantly. So when you're in a really big storm, the system is ballasted. So it just sinks below the surface until just the top of these towers is above the surface. And then the loads on it are greatly, greatly reduced. And so we can actually survive even the most extreme storms.
Are you generating power at that time?
Yes, ma'am. What you see inside here is effectively a spring and a generator. This is not complete, but it's close enough that hopefully you can see when I move this. We also have a lot of sensors in here looking at pressure, motion, etc., etc. But effectively, the generator would go here. But because this is a model, it's not in here. Actually, you can kind of see here, this particular one at the front here perhaps looks a little bit better. So this is at equilibrium. So the mass of the ring is fully supported by this spring. And so now any motion on top of that, i.e. wave-driven motion, causes it to oscillate around that point. And that causes motion at the generator.
So there are three separate generators.
There are three separate generators, and there's basically a key, there's a spring, and then there is a generator for each particular one. And it's the same, this isn't necessarily unique for us. This is a core method of generating power for two-body wave energy converters. You need a spring component and you need a generator component. Now, for small systems, you can use mechanical springs. For larger systems, you might need to use hydraulics or pneumatics. So some of our systems that we're building that are very small, we try and keep to mechanical springs. This is a 6th scale system. This unit was tested in Maine at the start of this year. Now, this is being decommissioned right now. So we tested this in Maine, it ran, and now we're pulling it apart to kind of see the areas where we want to improve for future.
How long was it in the water in Maine?
Just about a month. It did generate power, but just enough to power internal instruments and things like that. It was really just to test the dynamics and be able to use it to validate our numerical models. One of the main lessons learned is that it told us exactly what the sort of performance is going to look like. It taught us lots of things about working in the marine environment. You know, there's a lot of learning from, do you use this valve over this valve, or, how do you bond composites and aluminum? And there was a lot of lessons learned in that sense. But those are numerical estimates of the system match what we got in practice. And they were close, but they weren't perfect. So what we have here is it's a hydraulic system, and this is how we will generate power in our megawatt scale system. Now, because it's hydraulics, it always looks way more complicated than it actually is, because that's just how hydraulics seems to be. That cylinder acts as the spring, and that cylinder acts as the generator. Now, the smarts come in with how do you control it? And that's what we have in here. We have a series of mostly Siemens equipment with some supercapacitor storage for balancing. But ultimately, this allows us to be able to control the generator torque and the hydraulic motor swash plate angle in order to get the maximum power out of the system at all the time.
And would you need a box like this for all three?
Correct. They're independent.
So in the megawatt scale one, you're going to have three of everything we're seeing here.
It's basically duplicate. That's the storage, exactly, and then ultimately onto a bus, which then goes to the grid.
And are you doing DC out or
That will
AC
depend
out?
on the application.
Okay.
Megawatt scale converters, we wouldn't install just one. We would install multiple ones, just like wind turbines. So the power from those converters would all get aggregated at some substation offshore, which would then go via a large export cable to shore. So how you do that aggregation, that's an open question. One of the biggest challenges with wave energy systems is how do you extract the most energy from the environment? And you can do that, first part is what's the hydrodynamics look like? So what does the shape of the system look like, and how is it going to move with the wave? But then the next part of that is how do you apply the resistance to motion? Because in order to extract energy, you've got to put something to work against, your generator. And if you think about this, is that if your generator torque is infinitely big, you get no motion from the system, so you don't extract energy. If your generator torque is 0, you get lots and lots of motion, but no power on the output. And so you've got to find some happy medium. Now, if it was a constant, like a wind turbine, it was all rotating at the same speed, well, that's okay. You can ultimately, do all sorts of different well-known control approaches in order to figure out what's that point, and then operate there for a while until maybe the input torque changes. With a wave, it changes cyclically all the time. And so your control approaches are now quite different and quite complex. And so anything you do here in terms of how we change that torque directly affects how the device moves in the waves. And so it's a coupled system, and it's very complex. So there are simple approaches where you can use just a constant value for the damping, or we say damping, but ultimately we mean generator torque. So use a constant value, and then you'll get poor performance. You can use an approach called linear damping, where that generator torque increases linearly with speed. So the faster it goes, the more resistance you apply. The slower it goes, the less resistance you apply. And then there are other approaches where you actually have much, much more advanced control, where you look specifically at where in the wave cycle you are, and then you change it on a second-by-second basis in order to get a kind of a pseudo-resonant response.
And if you have all of the mechanics, the sensors and the control system that allow you to do it, it seems like something you could update on the fly with a firmware upgrade.
Yes and no. One of the challenges is that we're trying to build these systems to be as cost-effective as possible. So you always want to know what are your design maximums. And the challenge is that a lot of times, many of these strategies require you to apply large forces for short periods of time. That means you need bigger generators, or bigger parts of the system. And now you have to make a decision during the design process that, well, how much am I willing to spend on being able to implement these strategies. And so it's always a trade-off.
Yeah.
And so, yes, theoretically you can,
Yeah.
if you throw infinite money at having a huge system. And there's also the other trade-off, which is the bigger your generator, the heavier it is. And certainly in our system, one of the things that we want is a lightweight float and a heavy ring.
Right.
So the lighter the equipment that goes into the float, the lighter the generator, the hydraulics, et cetera, go into the float, then we can make more power.
The system that's in Hawaii right now?
A different system altogether, actually. So that's the Triton C. Same sort of technology, same principle of float and ring, but that one's designed to be 100 kilowatts. Ultimately, it could be grid connected like it is in Hawaii, but ultimately we imagine that that system will be a power at sea system, whereby it would have batteries located in the ring, and it would basically charge up those batteries, and then those batteries would be used to power some other load. That could be a boat charging or something like that. One of the things that we are looking at right now, we're calling it a micro Triton, is about a couple of hundred. It's basically it's a small buoy that's designed to be around about 2 meters or so in diameter, that provides power for oceanographic observations or any sort of monitoring application that you might want to do offshore without the ability to provide a cable to it. And so we're currently in the process of building that. We've got some components here, but not all. But what you can see first off is the drivetrains, which we have these that are being tested right now. So like all of our systems, we have three drivetrains. They're all independent. And these are the drivetrains that we are developing for this micro Triton system. This is the entire generator, and you can see it's a whole lot smaller than some of the other things that we've been building. So we actually have external springs in this kit. These are custom made for us, but these are actually, like I said, weight is important. These are actually titanium. So they're very light, surprisingly light for a spring of this size. So this is a titanium spring that's designed specifically to be, corrosion resistant in salt water and actually pretty light. This is now hanging from the float, and then the generator is attached to the top, and the reaction ring would be attached to the bottom.
Oh, so these are vertical,
Correct.
not horizontal.
Orientation, yes. So what we have on the poster here is our micro Triton, which is a very small sized oceanographic buoy that's designed to be able to generate power at any point in the ocean, specifically to power an onboard instrumentation payload. Uses the same technology same architecture as all of our other systems, in that we have a floating body on the surface that you can see here, and then the reaction ring hanging beneath that. And so the relative motion of the two bodies is what generates power. The main difference between these systems is that there is the generator is actually located outboard in these red circular boxes that are actually flooded. The generator itself is designed to operate in salt water. Now, this particular system is designed to host this large antenna, which is an offshore HF radar system, which is specifically designed for metocean sensing by a company called Kodar. And it supplements an onshore radar network, and it allows much greater coverage. So the system itself is able to provide about 100 watts of power to an onboard payload 24/7.
And that's including the solar panel.
So this is one of the key things that you can use solar to supplement wave, because the two complement each other perfectly. And that's one of the key advantages, even at a grid level, is how solar can complement wave seasonally. And also wind as well. All three of them can together combine to produce a much more reliable power to the grid. But there's a lot we're hoping to learn from this deployment in North Carolina.
And so when's it going in the water?
Well, we hope that it's going to go in the water towards the end of the year.
Oh, pretty soon.
Yeah. So the system itself is currently under construction. We saw the springs earlier. The whole system will be integrated here over the next month or two. and then it'll go to North Carolina. The big challenge is permits. So the location where it's going to go is about 13 miles offshore of Cape Hatteras in North Carolina. The permits haven't come through yet, so we have to wait until they come through before we can do the permitting. But we are told that they're getting close.
I think that's a theme on my channel, is that so much of the decarbonization challenges are permits.
It's true.
More than finances or technology.
And it's all about risk. You know, when you've got something new and untested and where the impacts are unknown in the ocean, in a protected space, you have to be extra sensitive about some of these things. So it's understandable, but it is frustrating.
I'd like to thank Tim for his time and hospitality, and I'll be keeping an eye on Oscilla Power. While there are no currently commercially viable grid-connected wave energy converters, according to Traxon, there are 184 companies working on them. So the chances are good that someone will succeed. And since 40% of the world's population lives within 100 kilometers of the coast, wave power can provide power to these cities without the need for long transmission lines. Turkey has plans to build the world's largest wave energy converter in the Black Sea using technology from Israel's EcoWave Power. The plan calls for the facility to eventually reach a not too shabby 77 megawatts, equivalent to 77 of Oscilla's largest devices. If you've learned something, please like and subscribe. And you can also support the channel by buying me a coffee. And please share this video with anyone you know who has gone up and down the ocean like one of Oscilla's floats.